Hi everyone, I am Ivan Feliciano Avelino, and I'm going to present our work on causal discovery from a causal decision-making context. The title of our work is Learning a Causal Structure, a Bayesian Random Graph Approach. The main author of this work is Mauricio Gonzalez Soto. First, a brief introduction. We adopt the manipulationist interpretation of causality. This paradigm can be expressed as follows. A manipulation of a cause will result in a manipulation of the effect. Therefore, a causal relation allows the evaluation of a change in the consequence given a change in the cause. Furthermore, we are working in causal decision-making context where an agent faces situations in which an action must be chosen in the presence of uncertainty conditions. We attempt to learn a causal graphical structure while using it to make good choices. So what does a good decision mean? That is discussed in depth in Mauricio's previous work, but we are not covering that in this work. Our main contributions are: we use graphs in order to model the uncertainty about the existence of causal mechanisms within a given set of variables. Second, we adopt a Bayesian approach in order to capture a causal structure through interactions with a causal environment. And finally, we conduct experiments to show the usefulness of our method to learn a causal structure while using it to choose the optimal action. Some important concepts that we should have in mind are the next ones. First, a random graph can be thought of as an object which starts with a set of vertices and its edges are added at random according to some probability law. Because we are doing a Bayesian modeling, we first identify the source of uncertainty. In our case, the source of uncertainty is the existence or not of a causal relationship between a given pair of variables. Then we model such uncertainty as the probability of the occurrence of an edge in a random graph. So our methodology consists of the following steps and assumptions. Let a rational decision maker or an agent consider the following set of variables x from x1 to xn, which are causally related by some unknown and fixed causal graphical model. The agent knows that she can only intervene one variable at a time, for example x1, and she does it in order to alter the value of some identified as a reward variable, for example xn. And the agent knows a causal ordering of the variables, which specifies for some but not for all the variables which other variables cannot be a cause of it. And we will form a random graph using the beliefs that the decision maker has about the existence of a causal connection between nodes in a graph. These beliefs, denoted by PIG, are real numbers between 0 and 1 that the agent has over a directed edge existing between the variable with index I and the variable with index j. This is an overview of our method, which requires as input the number of iterations. Each iteration corresponds to an interaction with the environment and the updating of the beliefs. First, which randomly initialize the beliefs. For example, Pij could be equal to 0.5. And at each iteration, we start with a DAG, where every node corresponds to one variable, and there exists a link between I and j with probability Pij. This could be thought as throwing a charged coin and connecting nodes I and j if head turns up. And to identify causal effects, the agent makes an intervention over the possible values of some intervention variable. The action selection could be random or by choosing the optimal action. And once the action is taken, a full realization is observed. Then, in order to update the beliefs, the current beliefs, according to what has been observed, we use Bayes' theorem as follows. For each pair of indexes I and j and the current graph, we ask for the probability of such graph producing the realization observed, which will be used as the likelihood of data given the current graph. As prior probability, we simply use Pij, so we have this update rule, and we update the model generating a new graph according to these new beliefs. This is repeated until the maximum number of iterations is reached. So we conducted several experiments, and we have as objective to show that the structure of a causal model, which controls an environment, can be learned via repeated interaction by a rational decision maker. We attack this hypothetical problem, the disease treatment problem, where we consider a patient who can have one of two possible diseases, and a doctor can treat the disease with either treatment A or treatment B, both of which carry some risk. Whether a patient is cured or not depends on the disease she or he is dealing with, the given treatment, and a possible negative reaction that the treatment may have on the subject. We propose to mimic the interaction physician-patient with an agent interacting with an environment which is ruled by a causal model. The underlying structure of the causal model is shown in the figure, in the left figure. And in the right side of the slide, we can see another graph, which is the graph with all the possible connections corresponding to the beliefs. And we can see that there are two spurious connections. So, because if an optimal action is selected at every step, then the decision maker takes the risk of not observing enough events in order to update her beliefs due to the exploration-exploitation trade-off. We propose to compare three different action selection policies. One is a random action selection policy, and the remaining two are based on the epsilon greedy method, which is similar to the epsilon greedy in reinforcement learning, where we begin with a high exploration rate, that is a high probability of choosing a random action, and we decay this exploration rate to a minimum such that at the end, just the best actions are selected with a high probability. So we decay the exploration rate in a linear and an exponential way, and this graph shows that the beliefs evolve when doing different interventions. In general, except for the middle plot, it is achieved what was expected. The correlate relationships, the four on the upper part of the graphs, converge to the higher values, and the wrong ones go down and tend to 0 or less than 0.5. And after a few interventions, the system learns the causal model and at the same time learns to choose the best treatment. To know how good is our agent at choosing the best treatment, we compare a proposal and its variants against the Q-learning method, which is a classical RL reinforcement learning algorithm, which is purely associative. We can see that the policy using the fast decay on our method on the exploration rate performs better than the rest of the methods, and it's very similar to the Q-learning algorithm with the same action selection scheme. However, our approach learns to choose from causal mechanisms of the work, and that gives applause to other associative schemes. So, as conclusions and future work, we have presented a Bayesian random graph-based methodology which is able to learn a causal structure from interventions. And our approach is flexible and easily implementable as shown by the experiments, where we learn the optimal action while also learning a causal structure. Finally, we assume the existence of this causal order, but in future work, we should relax this assumption. So thank you very much for your attention, and if you have any questions, we are here to answer them. Thank you.